we are discussing the optimization of the function z equals to f of xy subject to the constraint gxy equals to c. Okay. And we have obtained necessary condition for the points to be the points of local maxima or local minima. And that was by Lagrange method. So we defined the Lagrange function as follows. Where lambda was the Lagrange multiplier. Okay. And we saw that Lx equals to 0 and Ly equals to 0 with gxy equals to c are the necessary conditions. Okay. So when Lx was equals to 0, we got fx equals to lambda gx and we got fy equals to lambda times gy. Also, we assume that g of xy equals to c because this constraint is given to us. So when we differentiate it with respect to x, so we will get the partial derivative of gx dx by dx plus partial derivative of y, g with respect to y, dy by dx equals to 0. And from here, dy by dx, that was y dash was equals to minus gx upon gy. So we have this, this, and this. Okay. Now we assume that f and g have, second order continuous derivatives. Okay. So it is 2 times differentiable and it has second order continuous derivatives. That means fxx, fxy, fyx, gxx, gxy, gyy all exist and are continuous. Also, f of xy will be equal to f of yx because of continuity, and g of xy will be equal to g of yx. So this is the assumption that we will have. Now, the aim is to obtain sufficient conditions. The aim is to obtain sufficient conditions for a stationary point. For a stationary point to be a local max or min. Okay. So as in the first derivative case, when we have a function of one variable, what we do? We put the derivative equal to 0. The points obtained, the x values obtained are called the stationary points. Here, we put the Lx equals to 0 and Ly equals to 0 and the point, the x0, y0 point obtained by solving this, this, and this are called the stationary point of this problem, where we have to optimize a function of 2 variables subject to a constraint, equality constraint. Okay. So basically, this is what is happening. So now we are up using sufficient condition for a stationary point to be a local maximum or minimum. We are actually trying to derive sufficient conditions. So in the first derivative case, like the case of one variable y equals to fx, f dash x equals to 0 gave us stationary points. If f double dash x was negative, we got local max. And if f double dash x was positive, we got local min. Okay. So let's see what is going to happen in this case. Now, we have a function z equals to f of xy. And we know that y dash equals to minus gx by gy. And fx equals to lambda times gx. Fy equals to lambda times gy. Fxy equals to fyx. Gxy equals to gyx. Okay. So let us try to proceed. So now we have Z. So we will have dz, the total differential, that is equal to fx dx plus fy dy. So this implies that dz upon dx is equal to f of x plus f of y dy by dx. Okay. So now what is dy by dx? So that is fx plus fyy dash. So eventually what we are going to get, dz by dx equals to fx. Now in place of y dash, we will put minus gx by gy. So fy gxy gy. So now what we are going to do, we are again going to differentiate. So when we again differentiate, what is going to happen? D square z by dx2. So again we are differentiating. So we will again differentiate fxx. Then we will get fxy y dash. Okay. Then we will have minus gx by gy common. And then we will have fyx plus fyy y dash. Okay. And then we will have minus fy common. And then what we are going to have? Quotient rule. So we will have gy square, gy. Okay. Now we will differentiate gx. Gxx plus gxy y dash. Now we will have gx. So we will have gyx plus gyy y dash. So that is what we are going to have. Okay. So let us try to simplify what we have written. So what is going to happen is this. So d2z by dx2 will be fxx. Instead of y dash, we will write again gx by gy. Then minus gx by gy. Instead of fyx, I can write f of xy. Instead of y dash, we will again write minus gx by gy, fy, y. Then instead of this fy, we can write lambda times gy. Okay. And we will have gy square common. Okay. And now we will have gy gxx minus gxy gx by gy. Then again minus gx gyx. Instead of gyx, I can again write gxy plus gyy. Instead of y dash, we are going to have minus gx by gy. Okay. So again, one more line, simplify it. So d2z by dx2 is f of xx. Okay. And then we have this thing. Let us again cross-check the calculations. This is f of xx minus f of xy, gx gy minus gx by gy, f of xy. Okay. And we had lambda somewhere. Yeah. So this fy was lambda. Okay. So we have fxx minus fxy gx gy minus fxy gx gy minus fyy gx by gy whole square. Then plus lambda times minus lambda times gxx. Then minus plus gxy. Okay, so this is a gy and this gy will get cancelled out, and then here we will have gxy So we will have minus plus gxy. This gy and this gy will cancel out each other. So we will have gx by gy. So again minus plus, and then we will have, okay, this gy. So again we will have gx by gy, g of xy, and then minus. So that is minus lambda times gyy. Okay, and then this is going to be gx square by gy square. Okay. So now in the next step, we will have d square z by dx2 equals to f of xx. Okay, f of xx and minus lambda times g of xx. Then we will have minus 2 times f of xy gx by gy. So even this is gone, and then this is going to be minus lambda times gxy and again lambda times gxy. So this is 2 lambda gxy gx by gy. Then we will have minus fy gx by gy whole square minus lambda times gyy gx by gy whole square. So then d2z by dx2 will be fxx minus lambda gxx minus 2 fxy minus lambda gxy gx by gy, and then this is minus plus. Okay, so this should be plus and then minus. Okay, so then we will have fyy minus lambda times gyy gx by gy whole square. So d2z by dx2 will eventually become, if we take 1 upon gy square common, okay, so we are going to get fxx minus lambda times gxx gy whole square minus 2 times fxx minus lambda times gxy gx gy plus fyy minus lambda times gyy gx whole square. So this is equation number 1. Okay. Now, if we consider the matrix, or we consider bordered Hessian matrix. Okay. So what is that matrix? D of xy. So D of xy is this matrix 0, gx, gy, gx, gy. fxx minus lambda gxx, fyy minus lambda fxy minus lambda gxy. Then we have fxy minus lambda gxy, fyy minus lambda gyy. Okay. Now, this particular, if we look at this 2 by 2 matrix, if we look at this 2 by 2 matrix or minor, we see that this is the Hessian of the Lagrange's function. What was the Lagrange's function? F of xy minus lambda times g of xy minus c. So this is nothing but the Hessian matrix of the Lagrange's function, and that is why this entire 3 by 3 determinant is known as bordered Hessian determinant or determinant of a border Hessian matrix. Okay. So now, with further calculations, it can be seen that d2z by dx2 will turn out to be minus 1 upon gy square d of xy. Because this entire quantity inside the bracket is going to be minus of dxy. Okay. Okay. So now we know that if the second derivative for local maxima, second derivative should be negative. So this is equivalent to dxy positive. And for local minima, the second derivative has to be positive. This is equivalent to dxy being negative because of this negative sign. Okay. So these are the sufficient conditions to check whether a point is a point of local maxima or local minima, because once we have the stationary point, how are we going to confirm whether it is a point of local maxima or minima or not? So these are the sufficient conditions to make sure or to ascertain that the given point is a point of local maxima or a local minima. Now, we had discussed this problem where we were optimizing x square plus y square, okay, subject to x square plus y square plus xy equals to 3. We did a problem like this. This was g of xy, and we got 4 candidates. So one of the points was 1, 1, minus 1, minus 1. Then one of the candidates was root 3 minus root 3 and minus root 3, root 3. And here the value of lambda was 2 by 3. And here the value of lambda was 2. Okay. So now this is my x, this is my y, and this is my lambda equals to 2 by 3. So let us try to see whether we got local minimum or not. You can see that z equals to 2 here, and over here z is equal to 6. So we can check for one of the points. Let's see. So this is our matrix. Okay. So first of all, we will make dxy. So d of xy will be 0, gx, gy, gx, gy, fxx minus lambda gxx, fxy minus lambda gxy, fxy minus lambda gxy, fyy minus lambda gy. So first of all, we should calculate g of x. So g of x is 2x, g of y is 2y, g of xx is 2, G of YY is 2 and G of XY is 0. Okay. Also, F of X is, okay, this is for this is for F. This is for this function, X square plus Y square. So these are for F. Okay. For G, we will have G of X is 2X plus Y. Then G of XY would be 1. G of Y is 2Y plus X. So G of YY would be 2. And similarly, G of XX would be 2. So let's try to make this matrix simpler. This is going to be 0. And this is going to be 2X plus Y. And this is going to be 2Y plus X. 2X plus Y. 2Y plus X. Now F of XX is 2 minus lambda GXX. And G of XX is 2. Okay. Yeah. So we have 2 minus 2 lambda. And F of YY is again 2 minus 2. And G of YY is again 2. Now we have F of XY 0. So we will have minus GXY is 1. So minus lambda minus lambda. Okay. So now let us see what is happening at one of these points. Okay. So at 1, 1, 2 by 3. This is the value of X. This is the value of Y. This is the value of lambda. Let us see what the determinant is. So this is 0 and this is 3 and this is 3, 3, 3. 2 minus 4 by 3 will be minus 1 by 3, minus 2 by 3, minus 2 by 3. And 2 minus 4 by 3 is, lambda was 2 by 3. So 2 minus 4 by 3 is going to be 2 by 3. Yes. So we will have 2 by 3. So I hope the calculations are correct. Again, we'll calculate 2 minus 2 lambda. So that means 2 minus 4 lambda by 3. Okay, fine. So now let's calculate the determinant. So this determinant, now since this point is actually a point of minima, which we have already seen. So this determinant should come out to be negative. We've already seen the conditions. Yeah, this determinant should come out to be negative for maxima. So let's see. So let us expand along the first row. So you will have 0, minus 3, 3 minus 2 by 3, 3, 2 by 3, and then plus 3. So 3, 2 by 3, 3 minus 2 by 3. So this is going to be minus 6 by 3 plus 6 by 3 plus 3 minus 6 by 3 minus 6 by 3. So this is all going to be 2 plus 2. So that's going to be 4 minus 12 plus 3 and then again minus 4. So this is minus 24, which is negative. So dxy is negative and therefore 1, 1, 2 by 3 was a point of local minima. And this is going to hold for this point also. And at these points, this determinant will come out to be positive. So this is how we apply the conditions, the sufficient conditions to confirm whether our point is a point of local maxima or a point of local minima.